Okay, so if you remember me mentioning, especially when we first started learning about the different types of hydrocarbons we can have, benzene can change its name a bunch of times, right? So when it's a branch, when it has an alcohol group. So here's another one where we have a change in the name. So benzoic acid is actually the term used for benzene with a carboxyl group attached. So here is benzoic acid. So the carbons that are on the benzenes, you're probably wondering, well, why isn't the double bond OOH on the actual benzene itself? Remember that each of these are already occupied by quite a few bonds because we have the alternating double bonds. So really, each carbon in our benzene only has the ability to bond with one more thing. So when we're talking about a parent group with benzene, this entire structure is the parent. When we say benzoic acid, and of course, the carbon that has that carboxyl group that is bonded to it is always our carbon number 1. Okay, so that's going to help you with your next one. So here we have a diagram. Pause the video, give this a try, and try to name this structure. Okay, so hopefully you got, let me make this a bit bigger here for us, 2,5-dimethyl benzoic acid. So remember, we don't need a number for where that carboxyl group is. So we have here carbon 1, and then we still want to go in the direction that will give us the lowest numbers for our branches. So if we go to the right, we have 1, 2, 3, 4, 5. So our 2 methyl groups are at carbon 2 and carbon 5. If we were to have gone in the opposite direction, this would have been 1, 2, 3, 4, 5, 6. So 2, 5 is a better choice than 3, 6. All right, so try drawing this one. So 2,2,5 trimethyl hexanoic acid. Okay, so we have hexanoic acid, 1, 2, 3, 4, 5, 6. It doesn't matter which one you make your carbon 1, the one on the left or the one on the right. So on carbon, this is number 1 always. So carbon 2 has 2 methyl groups, and carbon 5, I believe, let me just double check, carbon 5. So we have 1, 2, 3, 4, 5. And of course, we fill in our hydrogens. Okay, so hopefully you are on the right track with this. Okay, so for just a few little fun facts. So a lot of carboxylic acids we mentioned have a sour taste. But actually, the ones that are liquid at room temperature, which is majority of them, have a very sharp odor, like a very distinct smell to them. So some of them are very unpleasant and some of them are okay. So for example, ethanoic acid is also one of the main active ingredients in vinegar. Vinegar is really typically just a solution, a dilute solution of ethanoic acid. Typically it's a 5% volume per volume solution. But, you know, think of what vinegar smells like. You would probably recognize that smell anywhere, right? Like a smell, like, hey, it smells like vinegar in here. So it's a very known smell to be sharp, almost like sour smelling too, right? Butanoic acid is actually one of the compounds that is in body odor, which is lovely. So that is usually the smell of what body odor smells like. So like unwashed socks, or, you know, underwear, or locker room. You know, let's say you play a sport and you leave your stuff in your locker or in a gym bag for like a week, and you go and you take a whiff of your bag after, you probably recognize the smell. So that's butanoic acid, and it's just something our body naturally produces. And I guess an additional fun fact is one of the main glands that actually excretes out butanoic acid is actually the glands that are found behind your ears. So it kind of reminds me of, there's an old saying that says to make sure you wash behind your ears when you're in the shower. And that's maybe that originally came from the fact that if people didn't do that, that it kind of had a smell after a while because of the butanoic acid. And then, of course, we have some stinky cheeses. So a lot of acids that are formed in cheese, especially cheese that has bacteria that's added. Most cheeses do have some amount of bacterial culture in it, but to make note of the real stinky cheeses typically is because we have some acid, carboxylic acid groupings in there. So hexanoic acid is just one example, but they're found in many stinkers. Okay, so let's look at reactions. So how do we do a reaction to prepare a carboxylic acid? Okay, so we're doing another oxidation reaction. So if you remember, we actually saw this before when we looked at the production of aldehydes and ketones. So in order to make an aldehyde, we have to have a primary alcohol that is being oxidized. So primary alcohol, meaning the OH is on a carbon that has two other hydrogens on it, and we're adding an oxidizing agent. So remember, that could be multiple things, a permanganate, it could be hydrogen peroxide. There are multiple different things that can be added. However, when you're writing out these reactions, you don't have to be specific in terms of which agent, but you're putting here a reactive oxygen, right? So when you have a primary alcohol that is oxidizing, our final compound ends up being an aldehyde. So meaning the location where the OH was is now a carbonyl group, and we have obviously the hydrogen that was removed is creating water. So really, this hydrogen and another hydrogen that is on that same carbon go onto the reactive oxygen to form water, and we have an aldehyde as a result. So what happens here is actually, if we were to continue oxidizing this aldehyde, so if we take an aldehyde and we oxidize it, that's actually how we are going to produce a carboxylic acid. Okay, so what happens here is actually, instead of removing atoms, the reactive oxygen goes essentially in between the carbon and hydrogen where that carbonyl grouping is. So it essentially will break that bond and go in between the C and the H, which would then, of course, lead us to having our OH group. So there's no additional products that are formed when we're making carboxylic acids. It's really just you're adding in that single oxygen. So if we go back to this, right, that's exactly what's kind of being shown here. So really, when we're doing this, so for this year, I guess in October 2020, when I'm recording this. If you're watching this in the future, we will be doing this. But during our COVID year here in our quadmester, where we're going to run out of time, we're not going to spend any time going through multi-step reactions. Okay, I wish we could if we had enough time. But anyways, I'm going to show you how they're done. I'm just not going to be expecting you to do this. So for example, here we have a two-step process. And this is actually how they create wine. I should say they create vinegar from wine. So you know how you can get red wine vinegar or white wine vinegar? This is essentially what the process is. So we have ethanol, which is the alcohol portion of wine, and it's oxidized. So over time, it oxidizes into ethanal, which is our aldehyde. If we were to continue oxidizing it, we then have our carboxylic acid, which is now our component in our vinegar. So to prepare a carboxylic acid, we really take an aldehyde and we oxidize it. So we went through those examples. Okay, so esters are our next functional group, and actually they are a lovely functional group. As much as I like carboxylic acids, I'm not really a huge fan of the stinkiness. I mean, don't get me wrong, I love citrus fruits and I love all the things where they're giving that sour taste. You know, every once in a while you want to smell something nice. So that's what an ester is here. So an ester is, again, remember I mentioned this at the beginning, it's a C double bond O with another oxygen, but there are carbons on the other side to this. So this is not a hydrogen like we just finished seeing. This is going to be another carbon-based group. So esters are responsible for some of the nicest smells that are naturally found. So different plants, different fruits. You're going to see also things like spices such as like vanilla, cinnamon, a lot of different nice smells that we like to have, or unless we have a sensitivity to smells, I'm sorry. But, you know, when you cut into a fresh pineapple and you get a smell, or you open a banana and you have that nice smell, part of the smells you are smelling are associated with these compounds that have esters in them. So we're going to go through and take a look at, of course, we'll look at everything we normally do. We'll look at reactions, we'll look at naming and properties. So, I kind of mentioned this already. So if you didn't know already, so a lot of the times when you are buying things in stores that are processed or have artificial smells added to them, such as hand cream or different cosmetics, lip gloss, even when you're doing, let's say you're chewing strawberry bubble gum. You know that that's not real strawberry in that bubble gum. Well, maybe you didn't, but you know now, okay, spoiler. But when you're doing this, when they're manufacturing, let's say that strawberry bubble gum, they want to use artificial flavors and artificial smells. So when they're doing that, they have to artificially make the same ester. So they are trying to mimic the same natural compound that would be in a strawberry, but we want to make it and manufacture it hopefully as cheap and quickly as possible so that we can add it to different products such as gum. Right? So if we had to extract from a real strawberry, your gum would probably be very expensive. Okay, it wouldn't be 99 cents. You know, maybe we're looking at, $4.99 or something like that. So hopefully you know that a lot of things are synthetically made in a lab, right? So the reaction that is used to create esters is called esterification. Okay, so sometimes it's also referred to as dehydration, just because a water is going to be produced in the process. So the reactants are always the same. We need a carboxylic acid and an alcohol. So what's going to result is we're going to have an ester and water. So here's the process. So our carboxylic acid and alcohol, so notice it also says and phenol, because it does not matter what the grouping is. What matters is it needs an OH group. So the OH from the acid and the hydrogen from the OH alcohol come together to form water. Okay, the resulting bonds that are made is the oxygen that we just removed the hydrogen from will essentially connect to the carbon that we just removed the OH group from. So that's how we get our ester. Okay, so as you can see here, there's a few things. This might look really confusing right now. First of all, the double arrow means that we can go in the reverse direction for this. We'll look at this in Unit 4. Okay, not now. Don't worry about this now. And you can see that there are catalysts and different things that have to be added to do this. Again, don't worry about this. I'm more concerned about you understanding the mechanism of this reaction.